Hello everybody, and welcome to another BCS Chester and North Wales meeting. Tonight we've got our AGM business, and then we'll quickly hand over to Professor Ian Morrison, who's going to do a talk on the history of computing at Jodrell Bank. So initially, for those who haven't met me before, so I'm Martin King. I've been the chair of the branch since November 2017. A couple of years before that, I sat as the membership secretary. And please do fire in some questions as well during the AGM. Obviously, this is our first webinar AGM, so we'll hope that the technology gods play with us and that the kids don't run in behind the scenes, but we'll see how we get on. So just working through our order of business, we've got some apologies sent through from Stuart Cunningham, who's one of our committee members. So I'm just going to accept the minutes of the previous AGM meeting. So if anybody can let us know if there is any problems there, please do let us know. But otherwise, I will take the silence as acceptance of those previous minutes. So just a quick run through the chair's report. So obviously, it's been an incredibly difficult year for quite a lot of different reasons. I suppose primarily we couldn't go any length into an AGM without talking about the impact of COVID-19 and the impact that that's had on not just the IT industry, but I think every industry right across the board. The BCS have been championing things like the vital IT workers, which have been well received across the industry. And I know that a number of people that certainly I'm in contact with have been part of that campaign and have been proudly showing off their badges on LinkedIn. I think if there was ever a time that you could see the impact that something like IT can have across the whole world, really, in terms of things like video conferencing, I would say that people are now more aware about things like video conferencing and FaceTime and Zoom than they have ever been in the past. And I think it does make me feel incredibly proud that IT has had the ability to change businesses overnight and make them remote working enabled, people still having calls and still making sure that they can carry on with business. And I think that's certainly a feather in the cap of the IT industry, and obviously a lot of the people on this call now and sort of in the broader BCS audience have certainly played a massive part of that. So it does make me feel incredibly proud that we've managed to have that sort of impact when things aren't going quite so well for the rest of the world. And even throughout that, one of the things that we have done certainly as a branch is that we've been able to extend some of our reach and our audience because of running our events via a webinar and having them recorded. It gives us the ability to reach a larger group. And because of that, we've continued with our events. Obviously, we had 11 events planned during the financial year. We did have to cancel a couple. One of them is actually Ian's from tonight, so we're going to be redoing that one. But we've had a massive range from data security, 3D scanning, threat hunting, Azure, Office 365, Teams, the impact of IR35, education tech, ERP, social media. I mean, we really have covered a massive amount of topics across all of our talks this year. And certainly, I hope you have found them as interesting and as exciting as I have. In terms of our focus for the next 12 months, that's exactly what we'll be trying to do again. We'll be making sure that we put on another year of great talks. We are always looking for new speakers. We're always looking for input into the sorts of things that you'd like to hear. So if there are ever any of those suggestions, please do send them through or get in touch through our LinkedIn group, Facebook. There's plenty of ways to get in touch with us. One of the parts that I'd just like to cover is around the inclusivity. The inclusion officer is a mandated role across the committee, and whilst, to be honest, we don't really have a nominated individual because all of us take it very seriously across the committee as well. So just to highlight a couple of the things that we have done around our inclusivity, we've had unconscious bias training. We have made as many adjustments as we possibly can to make sure that we can reach as many people as possible. And I think one of those things has been the transition to webinars, which obviously makes it inclusive across the board. But when we did have the in-person events, we had a range of different dietary requirements being covered. We made sure that the events were wheelchair accessible. All of the documents that were published were also made in formats that adhered to all of the accessibility standards and allowed screen readers and the likes to be used as well. And in terms of the dates and times of the meetings, we've tried to keep them as fixed as possible so that people can plan in advance. And we've also made sure that whenever we could, we recorded the events and also published them to YouTube as well. So I hope that you can see that we've been as engaged as we could possibly be as a committee this year. And certainly I would like to hope that that will go on for next year as well. And again, any inputs into that would be gratefully received. I'm quickly now just going to read out the Treasurer's report, which I just need to flick across into the other window for, because one of the things is that not everybody can speak if we've not set them up as co-organisers in advance. So I'm just going to quickly grab the Treasurer's report. So the quick upshot on behalf of Keith, because I know he's on tonight, but I'll just do a quick job in reading it out. It is available in the Dropbox pack, so the link that went out, it is available there. But what we have done is we've delivered, well under budget this year because obviously the impact of COVID and not having in-place events. So what we will do is send out a bit of a summary, but we have made a big saving and we've underspent roughly £1,326 across the financial year. But again, what we will do is we'll send that out as part of the pack, which is available anyway. We've applied for a similar budget for next year because obviously we don't know when things like the impact of COVID will be restricted. So again, we've gone in for a similar budget with the idea that that will change according to the response to COVID-19. Again, that is available if you'd like to read it as part of the pack that will go up online, and also it's available in the Dropbox as well. So bear with me a second whilst I get back to my screen. So now we've got the election of the committee members. So as this is a new way of doing things this year, what we're going to try and use is the raise hand function. So if I can ask for you to have a quick look as to the raise hand function, I'm going to try and point it out myself. It should be a button down that right hand side, and if anybody would like to point it to me, that would be great, because I'll be honest, I have forgotten. Okay, I'll tell you what we'll do. The main thing being that all of the roles that are mandated, so there's 3 roles which are mandated for the committee. So that's the chair, the treasurer, and the inclusion officer. So I am restanding for the chair role, and Keith Richardson is standing for the restanding for the treasurer role. There is nobody else standing for those. So unless there's any questions that want to come in, because you can fire them in, but if there's any questions or anybody who wants to stand against that, then please feel free to ping that into the chat. But other than that, you can accept that that is going to be the case, because I can't remember where the raise hand function is. Oh wait, there we are. Sorry, I can now see where the raise hand function is. Apologies. Okay. Do you know what? Seeing as I can't seem to get it too easily, technology's always going to be a trouble. What we'll do is we'll assume that these are taken as suggested, and if need be, we can always come back to that later on. Okay. I've just been reliably informed it's in the top right-hand side, but to be honest, the main thing being that we're a very inclusive branch anyway, and what we do have is the three main roles are sort of unanimously re-elected because there's no opposition. And what we've also got is 4 other committee roles, committee members. And if I just run through them, we've got Angela Best, who's restanding as a general committee member. We've got Stuart Cunningham, who's restanding as a general committee member. And then we've got David Lloyd Williams, who's restanding as our secretary. And then we've got Charles Ryder, who is restanding as the vice chair. So again, as nobody has put any nominations in to compete against them, we shall take them as unanimously re-elected. What we do have, which is very exciting, is 2 new committee members who have chosen to join us. So if I'll just give you a very quick speech as to what they've given to me. So we've got Professor Zendu Araya, so hopefully I'm saying that correctly, but otherwise known as Ezzy. And Ezzy has worked in the university and higher education sector since 2000. And before that, in the local authority as an ICT trainer. Ezzy was also a previous member of the BCS London Committee for several years before moving back up north in 2018. We've also got Gordon Richardson, who has been a BCS member now for 3 years and works at an apprenticeship training provider where they deliver the digital apprenticeship standards. He's also in the BCS Learning and Development Specialist Group, and he's also, as through his work, is a member of the BCS's Apprenticeship Provider Policy Group. Before that, obviously, Gordon, throughout his career, was a telecoms engineer before he worked in apprenticeships. And he also served in the RAF signals units for a number of years as well. After that, was an engineer and a manager in both mobile and fixed line telecom sector as well. As well as that, like that wasn't enough, he also likes to volunteer, and he volunteers with the Scouts, where he supports the adult volunteers across North Wales. So obviously, those 2 people have asked to join, and as we would always welcome new members, what we would usually do is have a vote to get those people on board, but for the time being, we will assume that we'll welcome them onto the committee because I can see David's posted there. So we can actually co-opt them onto the membership at any point. Now, obviously, I've now been waffling for a good sort of 20 minutes, and seeing as the polls are eluding me because I've had a busy day and not managed to figure them out, what I will do is now ask if there is any other business. So if there's any AOB, please feel free to bob it into the questions. And what we will do is, whilst we're preparing that, we'll ask Professor Ian Morrison to pop back in, and then we will take a couple of minutes just to line his talk back up.
Well, hi everybody, can you hear me?
Can indeed.
Oh good, I'm glad. You're not seeing me because I haven't used a webinar before. Oh, there we are. I can see some people now, and I didn't actually have any controls, but they've appeared again. And I just wanted to make sure that having got the screen up a few minutes ago, it was going to be there. So there we go. And I'm looking forward to giving you a talk a bit later on. So I'm sorry I'm not with you. I had been quite looking forward to coming across to Chester. I love going. I've given quite a few talks to Chester over the years, and I was hoping to come. But anyway, it's nice to be with you tonight, and I do hope you enjoy the talk.
Thank you very much. I can see that we've not had any questions. So I think all that is left to do is that if we just take a minute or so So we'll go quiet and we'll just get Ian all set up for you. Again, apologies that we've not managed to be as slick as possible tonight. But what we will do is, if there's any questions, please feel free to ping them into the chat or into the official questions section, and we will answer them. But what we will also do is, whilst Ian is talking, we'll collate the questions and then we'll pop back on at the end and we'll have a bit of a Q&A session. So that concludes our AGM business, and we'll just take a couple of minutes now to get Ian all set back up, and then we'll crack on. Thank you all very much.
Well, at the end of the talk, I'll try and appear so I can chat to you without just seeing a blue screen.
I'm sure we'll try and sort that out.
Yes. Okay, you can still see my screen, presumably.
I'm just going to pass things over to you now.
Do I have to show my screen, or can you see it?
I'm just going to stop sharing my webcam, and then you should be able to see.
I've got a sign that says show my screen.
That's the one.
I should click on that.
There we are.
Oh, jolly good. Okay, so whenever you're ready, I'll begin. Good evening, everybody, anyway.
Yep, no, if you want to crack on, I shall go on mute, and then I'll reappear at the end, and we'll have some questions. Thank you very much.
Well, that's a pleasure. Good evening. Very sorry I can't be with you tonight. I first gave this talk in Manchester to the group there, and it seemed to go down well, and they then asked me to go down and give it in London, which I did some time ago, probably last November, I think. And since then, both Chester and also the people at Rugby have asked me if I would actually give the talk to them, and maybe at the end of December I can go down to Rugby and give it in live form. Anyway, it's all about, in principle, computing at Jodrell Bank, but it would be silly to do that without giving you the context. So it's partly the story of Jodrell Bank and some of the nice things that have happened, but also, of course, how over the years, and quite a long period of time now, our computing has changed. And as you'll see, sadly, I was involved with quite a bit of this for about 20 years, and that's perhaps the most interesting bit of what happened. So let's begin. Let's hope that works. Okay, the story really begins just before, or at the start of the Second World War. Bernard Lovell had been studying cosmic rays at the University of Manchester, and he was sent to actually help develop radar during the war. He got the OBE for his work. And he first went to a place called Staxon Wold in the hills above Scarborough, and he was there the morning that war was declared. He saw echoes on the radar screens and got very perturbed because no one was doing anything about them. He said, well, why aren't you trying to scramble any fighters? And I said, those are echoes, but they are not aircraft. We do not know what causes them. They come and go a bit. We call them sporadics. Now, Lovell knew that a very high energy cosmic ray could give rise to a shower of electrons that could reflect radio waves. And he thought, therefore, these might be the result of high energy cosmic rays coming into the atmosphere. So when the war ended, he got hold of some army radar equipment. He tried it out outside the university buildings in Manchester. At that time, there were trams going up and down Oxford Road, and the interference was terrible. He found out that about 20 miles south of Manchester, a place called Jodrell Bank, a little hamlet, there was a couple of fields where the university botany department were doing some tests. And that's a picture of some of the radar equipment that he put outside the two wooden huts. And just notice that little sapling on the left. I'll tell you, that now totally envelops that left-hand hut. You cannot see it. Well, they managed to get echoes quite quickly. And it wasn't long before they found out they were nothing to do with cosmic rays, but were in fact echoes from meteor trails, as you can see on the right-hand side. That's a picture of the Leonid meteors, and we have a chance to see those in the next few days, in fact. The peak is on the 14th of November. I don't think it'll look like that, though. Well, that wasn't what they wanted to do, but it was interesting. So that work carried on and expanded. And after a while, the university got hold of the second field beyond. The one on the lower right here is where Lovell was, and they built the Jodrell Bank experimental station. There are quite a number of antennae there, or aerials, one of which was the searchlight aerial, which you might be able to see there, and that was very useful. It could look all around the sky. It was fully steerable. But in fact, the largest telescope is there, but you probably can't see it. It was called the 218-foot transit telescope. It's actually over here, but because it was a wire mesh surface, it's invisible. But perhaps you can see the little white dot there, and that is where the radio waves coming from above were actually focused. Now, you might think a telescope that's just looking directly overhead isn't much cop. But of course, as the Earth rotates once every 24 hours roughly, the sky comes overhead. So you actually can make a radio map of a strip of sky directly overhead all the way around. And by tilting the mast, as you can see in this image, you can actually make the next strip and the next one and the next one. So over a period of time, they could make a radio map of the sky, probably 30 degrees across, covering quite a strip of the sky that's roughly overhead at our latitude. And they made some very interesting discoveries. They discovered for the first time the radio emission from Tycho's supernova of 1572. It was visible for about a week or two in broad daylight, but now there's no optical evidence of it at all, but we found it in the radio. That's not our picture, by the way, that's a much more modern one. So that was good. Perhaps more significant was the fact that they were able to make a radio map, a very crude radio map of the Andromeda Galaxy, our nearest giant galaxy, 2.5 million light years away. And this proved for the first time that we were able to detect radio waves from well beyond our own Milky Way galaxy. Well, Lovell realized that if only he could have a telescope of that size or even bigger that could look all around the sky and also track objects, because then you could integrate up the signal, it would be a wonderful instrument to have. And so he got Charles Husband, a bridge engineer from Sheffield, design what was to become the Mark I radio telescope. And I have to say, I'm not that impressed with his original design. You can see that the whole bowl is actually supported at just 2 points about which it has to rotate. That doesn't give you much control. Now, at that point, the dish was going to be also a wire mesh, so it wasn't too heavy. But for various reasons, one of which may have been military, it was given a wire mesh dish. And therefore, the whole backing structure had to be much stronger. Anyway, some of you may have seen a film of the Tacoma Narrows Bridge disaster, when under steady winds, not gusty winds, it actually started oscillating and broke up. Lovell gave a talk about this telescope at the National Physical Laboratory in Tellington. And afterwards, a scientist came up to him and said, Bernard, or Sir Bernard, he wasn't Sir then, but Dr. Lovell, I suspect, he said, have you put a model of your telescope into a wind tunnel? And Lovell said no. He said, I think you ought to. So they built a 10-foot diameter model of the telescope, they put it in a wind tunnel, and it lasted about 5 minutes. It started oscillating just as the Tacoma Narrows Bridge did. So the telescope was redesigned, and it was given what we actually call it the bicycle wheel, but the wind stabilizing girder, which you can perhaps see under it here. And that basically added some friction so the telescope wouldn't oscillate. So that's a lovely picture of the telescope as it was first built. It was actually photographed from above the original transit telescope that you can see. Now, just out of context really, because there's a picture, I'd like to point out that little dish there. That was a 50-foot dish. Now, you may remember the Eagle has landed in Apollo 11, and we were using that dish to track the spacecraft as it landed. And this is the track we got, a Doppler track. Now, the Eagle was coming down under computer control, very smoothly deaccelerated as it came towards the surface, and that you can see in the red line here. But Armstrong realized they were about to land in a crater, so he took manual control. He lifted the spacecraft a little, you can see the bump just here, and then maneuvered it over the surface to land at that point there. And the point there is the Doppler is changing very slightly as the moon is moving around the Earth. So I think that was pretty damn good proof that the Eagle did actually land. And I don't understand how they had all this possibility of faking. In fact, Fox Television, not my favorite television station, actually had a program in about 2002 saying it was all a fake. And the following year, Canadian television said, no, it wasn't. It was all real. And I was actually on that program, And I described this particular plot intercut with Buzz Aldrin saying what was going on, and it fitted like a glove. So a nice little bit of history of Jodrell. Now, this was the control room as it looked at that time, and the telescope was driven by an analog electromechanical computer, which is on the left-hand side. Also over on the right, there were displays of the time, and that's very important, of course. You set up the source positions you wanted to observe with dials on that control desk, and there it went. But at the time that this was being built, Jodrell was in terrible straits. The money had run out. Lovell was about to be sued by her husband for non-payment of fees. The engineers commissioning the analog computer system walked off site. They were not being paid. And we were saved, happily, by the launch of Sputnik 1. And it was realized that our telescope, given a powerful radar, might be able to detect not the actual Sputnik, but the rocket that put it into orbit, which was following it behind it. And so the military obviously rang up various people. The engineers came back. They commissioned the telescope in probably working 24 hours a day. And it wasn't long before, with two powerful transmitters linked to the telescope, a very big cable was supplied by British insulated calendar cables to actually get the signals to the focus. And only a couple of weeks after it was launched, we were able to detect Sputnik's 1 third stage rocket, which was following behind about 200 miles behind, and it was actually going over the Lake District at the time. And there is Lovell showing the trace on we got with our radar system. And so the telescope stopped being a white elephant, and people realized that here in the UK, we had something that no one else in the world had. And for quite a while, it actually played a major role in what we might call space tracking. And we actually were asked by the Americans to control and bring back the data from some of their first rockets, which was very interesting. Now, some astronomy. The most important project, I think, that was done with the Mark I telescope in its early years was when the signals from a remote telescope, you can see it's mobile, it was taken around the countryside, were brought back to Jodrell Bank by a microwave radio link and combined with those of the Mark I telescope. This enabled us, over a period of a few years, to measure the angular sizes of about the 300 then known radio sources. And it was discovered that about 7 of them had angular sizes so small that on a photographic plate they would look like a star. Hence their name, Quasar, quasi-stellar object. It was first thought that they might be rather interesting stars in our own Milky Way galaxy. But in fact, I've gone the wrong way. In fact, when we made some observations again using this telescope at Defford, it was found we got a fairly accurate position. And when that was photographed, it was seen not to be a star because you can see that jet coming out on the lower right. And in fact, our radio image we had at that time showed you a core, very small core, and a jet, and it fitted like a glove. In America, they were able to take the spectra of this object, and it was shown to be 2.5 million light years away, so 1 million times further away than the Andromeda Galaxy. It was very bright, and I can actually image it with my 12-inch telescope in my back garden. So how could all that energy be created? It turns out that nuclear fusion isn't really good enough, and it was surmised that at the heart of this object there might be a massive or supermassive black hole, and as matter falls into it, it releases a vast amount of energy, and that seems to provide, and no one quite knows how, jets, 2 opposing jets. And if you happen to be somewhere along the line of that jet, you see a very bright object. So I think we probably discovered, or at least surmised, that at the heart of some distant galaxies there were supermassive black holes. In those days, our computer that we could use for analysis was the Atlas computer in Manchester. I think that's the Manchester one. It's not totally sure. And the first thing I did as a young research student in 1965 was to learn Atlas autocode. And we used to use that computer to do you know, to learn how to program. That was quite wonderful. Now, this I don't think is a picture of the Manchester one. I think it might be at Culham. But I want to point out that on the front left, there's a link. And essentially, we had one of these at Jodrell Bank. And so we could actually punch cards, put them in our end of the link, and they would appear at this end, at Manchester. Now, we shared that link so that in the daytime we used it, but at night time it was used by atomic power constructors in Sutton who were designing the Dungeness B nuclear power station. It so happened my girlfriend, now my wife, was actually doing some of the shielding calculations for the reactor. She was due to drive up in her Ford Popular one Friday afternoon, but we had a blizzard and I had to stop her coming. So I actually typed out a message on punch cards. It was sent up to Manchester and they forwarded it down to Sutton. I think that might have been the first email that was ever sent. I don't know, but it would be fun. Well, let's come back to Jodrell. The second telescope that was built at Jodrell Bank, large one, was the Mark II radio telescope. It's elliptical in shape, but effectively it's a 25-meter telescope. And this was the very first telescope in the world to be controlled by a digital computer, a Ferranti Argus 100. And that's a picture of it there. Quite a slow computer, but nevertheless it did the job beautifully well. Had a very nice control panel there. In fact, to make it work, you had to first of all hand load a very short program called the primary tape input program, which would then read a much bigger program, the control program, from a paper tape. And I think that was a two-stage process as well. So that was our Mark I. Sorry, our Argus 100 computer. And there you see all the actual units that made it up. As I said, it needed a PTI program to be hand loaded. And I do remember the multiply was incredibly slow. If you wanted to multiply by 10, it was quicker to do a shift by 1 to give you twice the number, then 2 more shifts to give you 8 times the number and add them together. As a subroutine, it was better than actually multiplying by 10. Okay, I was given probably the most horrendous PhD project that anyone's ever had at Jodrell Bank, and I'll explain why in a minute. It was to help build a lunar aperture synthesis radar, to use just a 50-foot dish to synthesize a 40-kilometer wide dish to image the surface of the moon by radar. And the idea was to observe at 75 and 185 centimeters, quite long wavelengths. And it meant that we were sensitive to detect boulders and things of that sort of scale size on the surface. So I joined the group in '66 following a term of lectures and lab work, and that was basically my downfall. As part of that lab work, I was presented with a board with I think 100 or so logic gates on it, 2 sets of switches and some lamps. Said, make something work. And somehow I made it multiply, 2 4-bit numbers. And sadly, that impressed them rather a lot. And that's why I was given this horrendous PhD project, which was to design and build a hybrid computer to act as a receiver system for the radar. And of course, that means it's part analog. I designed that. That was quite easy, but also part digital. And we could not afford a digital computer. So what happened? I was given the Argus 100 manuals, which explained very well, in fact, how it worked. I had to learn how it worked, and then I had to design and build an equivalent computer, which I did. We called it, it doesn't matter what we called it, doesn't matter. Anyway, we called it. So it was a 24-bit serial computer like the Argus, and essentially used the same autocode, same control commands. I used much faster logic. It was now transistor diode, and I gave it a fast multiply algorithm, and it could divide. And I didn't think that the Argus 100 could divide, but someone told me it could, so I was probably wrong. And in fact, we put into a little bit of read-only memory the PTI program, so you didn't have to put in a program by hand. Initially, we had a 4K, only 24-bit core memory, but we actually got a very big memory, one of the largest that Manchester had at the time, from an insurance company in London. Now, sadly, even that would not be fast enough to actually do what we had to do, which was to correlate the data being collected by our telescope. And that would be the inner loop of the data acquisition. So to get over that, I added a specific correlate instruction, and that compared to 24-bit words to find the number of equivalent bits between the two. They were counted into a counter, which was 0 to start with, and then we could read it. So we had two instructions, one to do the comparison, one to read the number. So that made it very, very much faster in its inner loop, and it was capable of doing the work. And it did work. That's a radar map on the right-hand side. I mean, the resolution is very low, but it's pretty amazing for the time. And you can see this very bright spot here. That's the crater Plato, which is that one there, and that one there is Copernicus, which is there. And it basically showed, and this was at the time of Apollo, which parts of the lunar surface were scattered with boulders and which were very much uniform. And in fact, this dark bit here is in fact where Apollo 11 landed. So perhaps it was of some use. Well, in 1972, the telescope was extensively rebuilt. There was metal fatigue at the tops of the towers. So to take the weight away from the towers, they added these two semicircular girders. Now, to keep it balanced about the center of rotation here, the axis, they had to put in a new surface, which was shallower, which made it more efficient, and also smoother than the original. And can I just mention this little hut down the right here? It's called the Marconi hut. That housed a very powerful transmitter. And between about 1960 and 1963, something like that, which included the time of the Cuban Missile Crisis, that in fact was the UK's early warning radar. And during that crisis, I'm told, I wasn't there then of course, but it was actually on the horizon pointing towards Lithuania, because our spies had told us that that's where the ICBMs aimed at the UK were housed. And I was very pleased that James May went there in the program a couple of years ago and was actually shown one of the silos that the Russians had used. So we did play a little bit of a role in the defense of the realm, but happily never in anger. Now, we controlled that by transferring the Argus 100 from the Mark II telescope to control the Mark I, then called in fact the Mark 1A telescope. Now that's a horrible name. On its 30th birthday, we renamed it the Lovell telescope, and that's what I shall call it from now on. Okay, so the 100 was moved across, and we brought two further Argus 400s, much more compact, but still serial machines. One of them was used to control the Mark II, as the 100 had done, but also it was powerful enough to actually carry out the data acquisition as well. And the second one was used to acquire the data from the Lovell telescope when we used that with it. So two very useful computers. Having completed the upgrade, Lovell asked his staff, what can we do with it? And Dennis Wall said, well, let's make a survey of a part of the sky, a sensitive survey, to see what interesting radio sources we can find. And in that survey, they discovered what looked like a little peanut. It was in fact something we call the double quasar. It's slightly blue there. In fact, quasars do look a bit blue. Very close together, 6 arc seconds apart. When images were taken that with the world's largest optical telescopes, it was discovered that there were 3 objects there. The top and the bottom, you can see some spikes. That actually is a diffraction effect. They were point sources. They are quasars, very far away. The one just above the lower one, is much broader, has no spikes. That's an intervening galaxy, about halfway between us and the distant pair. When they took the spectra, the signatures of these 2 quasars, they were discovered to be identical. We don't believe they're identical twins out there in the universe, so what's going on? Well, it's all down to Albert Einstein, a lot's down to him. Basically, the gravitational effects distorting the space-time around it of that galaxy actually produces what's called a gravitational lens. And this lower image here, that one, is just another image of that one there. So we see it twice. But I think you can see the light path and radio path from the top one is direct to us, this one. But here it's gone down, being deflected up to us. And that path must be longer. And it's 431 days longer. So the path difference is 31 light days. From the geometry and that time, we were actually able to make a measurement of the expansion rate of the universe and got a value with rather large error bars of about 68. Now, at that time, the optical astronomers, one group had about 50, one group had 100. But over time, those numbers have converged. And I think the best value what we have now is about 68.7 or something, although there's some controversy. So we did a good job with that. Excuse me, I've given one talk already today, so my voice isn't as good as it should be. Now, I was promoted to be a lecturer virtually as soon as I'd done my PhD work, which was very nice because these days that doesn't happen. But that was largely to help with the development of the computer systems at Jodrell Bank. But they did let me out to do some astronomy. I mean, I was really a radio astronomer. And I used the Mark I along with another telescope called the Mark II, the one on the left there, which was meant to be portable. It never actually moved, about 24 kilometers to the southwest of Jodrell Bank near Nantwich. And with that, we can actually observe quasars, or we could, and we could analyze the data, not to make pictures, but to get an idea of their structure. And we needed a computer to do that work. And it had to be giving you a visual feedback so you could see what was going on. And it had to be pretty accurately done. In order to make it work, you had to measure the path length between the two telescopes, which was changing all the time, to about a precision of 2 centimeters. So we had a radio link, and they'll come back up later. We sent a signal out from Jodrell Bank, a pulse, shall we say. When it came back, we could measure the time. Actually, we measured the relative phase. Now, that obviously would be twice as much as would change from the signal just coming from Wardle to us. So we used that to align the data from the two telescopes, and that's how it worked. Well, they asked me, and I don't remember much about this, to build a computer that we could use to do its analysis. So I made a 24-bit computer just based on the Argus instruction set, but that was made using TTL logic, which was around then. But I added a 48-bit stack-based floating point processor. A friend of mine was working on KDF9. They had one at Newcastle University. I thought that was rather good. So that we used for some years for radio source modeling and also for hydrogen line analysis using the Cooley-Tukey Fourier fast transform that some of you may remember. I actually understood that, and the only really bit of important software I ever wrote in my life there at Jodrell was in fact a program to actually carry that out on that computer, and that was used for quite a few years. But basically I was a hardware rather than a software person. Now, another nice little bit of history that happened about then. You've heard of black holes. How can you observe them? Well, it's not easy, but if matter is pulled from a companion star onto what was called a white dwarf star, when the amount of matter makes the mass of that white dwarf sufficiently large, you get a massive X-ray flare, and that makes its presence known. So that's the idea. There's material being pulled from a star that's actually expanded at the end of its life onto this white dwarf star. Now, in 1975, Ariel 5 discovered the largest X-ray flare that has ever been observed, I think, or since. It came from a point within the constellation Micro-Circe, which you probably haven't heard of. It's just to the left of Orion. And this is, in fact, the flare. And the Crab Nebula produces flares down here. The biggest one we knew then was Scorpius X1 about here. But look at this. Now, notice it started going up rapidly around the 8th of August, 1975. Now, what do astronomers and university lecturers do in August? They go on holiday. And every member of the academic staff at Jodrell Bank was on holiday except me. That's not because I was a goody-goody. In those days, Macclesfield had its annual Barnaby holidays at the end of June, a much nicer time to take your holidays. So I'd had my main holiday already, so I was there. On the afternoon, I think it was the 9th, I was rung up by the professor at Loughborough University, where they were doing this work, Leicester, saying, we've discovered this flare in Micro-Circe. We don't quite know where it is. Can you search for it using your radio telescopes to try and find its position? Well, we used that Mark II, Mark III interferometer to survey the area of Micro-Circe where the X-ray source was detected. They told us the approximate position. In those days, we had paper tape charts, and we had a chart that when we printed it out was the width of the laboratory, about 20 feet long. The center was where they thought it might be. We actually discovered it 2 inches from the end, so we were dead lucky. And then refining our system, which we could do once we knew where it was precisely or closely, we got a very precise position. So we found out exactly where, I can't spell minutes, I'm sorry, exactly where it was. And then they could find out, you can't see the black hole, which we thought it was, but they could see the star, which was rotating very rapidly about this unseen object. And from that, you can calculate the mass of the companion, 9.7 solar masses, and that's got to be a black hole. I think it's still the nearest black hole to the Earth, about 3,500 light years away. So that was actually a quite fun little thing that we did with our interferometer. Lovell had hoped to build what was called the Mark V telescope. This was in the early 70s, and you remember the inflation, and the costs went up and up and up, so it was cancelled. But instead, we were given some money to build what was initially called the Multi-Telescope Radio-Linked Radio-Linked Interferometer. A horrible name. We wanted to call it Merlin, but Lovell wouldn't let us because there was some other system called Merlin. But as you'll see later on, we changed the name to Merlin. And we were allowed to build 3 new telescopes, one nearby at Tabley, one at Darn Hall, which is near Nantwich, and one near Knockan. And we also used that telescope I showed you down at Defford. So that was our system initially. Now, we had a problem. Ferranti had stopped making the 24-bit Argus computers. And the American control computers in those days were about 16 bits. Our encoders were about 18 bits in precision. And we needed 48-bit precision to carry out those phase calculations that are absolutely critical, without which it could not have worked. Now, a bit of interesting, I don't know, luck here. You may have heard of AMD. They build large numbers of processors for laptops now, don't they? But in those days, they were building very high quality interface circuits. And I've been using those to interface the encoders on our Mark I telescope and the Mark II telescope to bring the data down to our computers. I got rung up by the people at Quandon, the UK distributors, saying, we've just been given a set of data sheets. We have no idea what they're about. Will you look at them and come over and have lunch and tell us what they're about? So I looked at them, and I realized that was the fateful phone call I got from Cornell Electronics. These were the chips, the AMD 2900 series chips that some of you may be aware of. They were based around a 4-bit cascadable register arithmetic unit. That was the 2901. And it contained 16 registers just like Argus. I wondered whether someone from Ferranti had joined AMD and helped its design. And that's just a slice of it. It did lots of clever things. You can see it's a micro-coded machine and a 16 register device with all the arithmetic units you need for 4 bits worth. So the chipset included support chips to enable a micro-coded computer to be built with any word length, which is a multiple of 4. And of course, we had been using 24-bit computers. And I realized it would be very easy to design and build an Argus clone. It was a lot easier, in fact, than having to rewrite all of the Argus assembler code that we've been written over the past 10 years. Well, I designed it. Much of the work was outsourced. Remember, there'd been a computer called Circe. We call this one Micro-Circe, and we actually built 9 of them. And that's a picture of the back plane. It's the only one that's left, I think. Just notice that the date when it was commissioned was the 11th of the 4th, 1978. And you'll see what it was used for. We took it out of commission in 2018. I'm not sure many computers had a life that long. The bit that mattered here, the arithmetic unit, 3 boards, each with 8 bits on, 2 of the chips is here, all the control circuitry was here, and here's the memory system. And in those days, the memory cards were just 1K bits we used, 24 chips per board. That was the front panel, very much like the Argus 100 panel, you can see there. We built two for the Lovell telescope because Lovell wanted some redundancy, so they could actually switch between them if one failed. I don't think they ever did, but they could do it. There was one for each one for each of the other telescopes, one to act as the overall telescope control and communications computer at Jodrell, and one, a very important one, the one that's still there or was there until 2018, was to control the synthesizers and carry out all the phase measurements which were vital to enable us to link the telescopes up coherently. We developed the software in RAM, and when we were happy that we had a good system, we burnt it into ROM because the telescope engineers were really very scared about having a computer running remotely, which they couldn't control in any way at a distant site. So one thing we did, obviously you can get glitches and power things, so we devised a remote reset. So over the Tarity phone line, if a FAR computer failed for any reason, we could at least use it to implement a remote reset. And that we had to use a few times, as you can imagine. Well, we also needed a computer to actually run the whole system. And that had to do an awful lot of precise calculations. So we actually made a modern version or a newer version of that original Circe F. We called it Micro-Circe, to have the same 24-bit fixed point unit as the Circes, the earlier ones, Micro-Circes, and then I added a 48-bit stack-based floating point unit as before. That proved to be highly important. We actually built two, one to act as the overall MTRLI computer, as it was then, control computer, and one for the data analysis. Now, Professor John Davis, who was in charge of the project, decided to use the language called Forth, which some of you may have heard of. I would call it a write-only language, because once you'd written it, it was jolly hard to decode what on earth you'd done. Okay, it was developed by Charles Moore to control a radio telescope at the National Radio Astronomy Observatory at Kitt Peak in Arizona. It was an interpretive language, so you could port it very easily on new machines, and I think some machines are still using it. It used a stack-based architecture, and the basic stack-based arithmetic functions were used by subroutines were called words, and they're called words. So now it runs a Forth interpreter, and that adds quite an overhead over a fully compiled program. But there's one enormous advantage, and without it, I'm not sure we could have actually made Merlin work. You can modify words on the fly. If we found that part of the control system wasn't quite right, we could recode it, we could just retype it out on our computers as the whole system continues to run. And then in a little bit of free time, because you've obviously got to have some free time every second, we could replace the bad word, the faulty word, with a new one. And we didn't have to do any recompilation. I think without that, we'd never have managed to make the whole thing work. And in fact, John Davis and I were sitting there for, in fact, many months getting the whole system going. But we found out that our new machine wasn't fast enough. But I perhaps only had one little sort of moment of inspiration, a flash of light in my life. And I realized that because it was a stack-based machine, I could easily microcode the majority of the basic Forth words. So in effect, I taught Circe F Forth. I don't know whether other computers were able to run higher languages then, I don't know. Anyway, we could still therefore run Forth programs, most of what we had to do without using an interpreter, and that made a major increase in the overall speed. So it was okay. Well, in 1992, we upgraded Merlin. We added a further telescope, as you'll see, at Cambridge. It made the whole array now 217 kilometers across, has the same resolution in the radio as the Hubble Space Telescope does in the optical. And there you have the Lovell telescope in the background, the Mark II in the foreground. I spent a lovely summer, a little village called Knockin, close to the English-Welsh border. And this was the first of the new telescopes we had to commission. So that was a great summer. It was a lovely summer too. And every lunchtime, we'd go down to the little local shop and get ourselves some nice things to eat. It had a very nice range of sandwiches, I remember. Anyway, that shot went under new ownership recently, or not, actually not that recently now. He put up a big sign. So that was the knock-in shop we used to go to. Well, that's the lovely 32-meter telescope at Cambridge, and that is also used, as you'll see, in our European array as well. And that will come back to that. A lovely telescope. And these telescopes, we were able to fit a carousel inside the receiver room, which is sort of under here, so we could remotely change the wavelength that we were observing with. And that's the knock-in telescope. You saw it before, it now has been painted white. You can see the dish here, which is used to send the radio signals collected by the dish back to Jodrell, and a smaller one up here, which was part of that radio link system to measure the phase. If we use the Lovell telescope, it doubles the collecting area. And that's the phase transfer system, and that requires a 1 picosecond stability over 250 kilometers to maintain our coherence at 22 gigahertz. And that's why we had to make some very precise measurements. And just to the right here, you can see that Micro-Circe machine that we used until about 2019 for that job, 2018. Internally at Jodrell, we had an interesting little comm system, but control linking system between the telescopes, the three computer systems. There was just one cable terminated at each end, and a polling system would basically say, your turn, your turn, your turn, at which time, if one of those three computers needed to send us some information to the others, like every second the telescope control computer would tell all the information about the telescopes to the control computer on the right there, and also the L-band link would need to do it. So basically, two things. One is you never got any clashes because each one only sent its messages when it was told to. And secondly, it was totally separate from the outside world. No one could hack into it. There was a way out, so we could take all the data from the telescopes and show them on normal computer screens elsewhere. But it was in fact hack-proof, and I think it really was. So there's the link tower at Jodrell. You can see that in every direction there are two dishes. One is for the radio signals coming back, one for the L-band link. A very nice image there we took with a double quasar. You know, I remember the two stars, the two quasars, one there, and that's actually very faint, the galaxy. So it was a good system. Now, at this point, we started getting some real computers in at Jodrell. The first one we had at Jodrell was an AVAX 11780, and we had an AP120B floating point coprocessor, which you can see a picture of down on the lower right. So that was the first powerful machine we actually had at Jodrell Bank. And then we had a grant to buy a mini supercomputer, and we had an awful tussle between Alliant and Convex about who should actually sell us the mini supercomputer. In the end, we actually got an Alliant one. I've actually got one of the main boards in one of my rooms, just as a memento of that. So that was used for doing an awful lot of the analysis of the Merlin data. And we went over to using Sun workstations for control. So all of my stuff that I built over the years obviously became redundant, not to worry. Now, pulsars is something that the Lovell telescope has been a major investigative tool over the years. Our sun is producing its energy in its core. That will finish converting the hydrogen to helium, which produces the energy, in about another 4,000 million years. At the end of that time, the star changes amazingly. The outer parts will probably, in fact, engulf the Earth. And in the heart of it, the helium which is being produced is converted first into carbon and then into oxygen, and maybe a bit of sulfur. At the end of their lives, these stars blow up. And a star like our sun will blow off its outer parts containing many of those heavier elements and leave behind this little dot you can see. This is the Ring Nebula. Now, that is basically the core, the dying ember of the nuclear fusion core. It's very hot, it's very small, it's about the size of the Earth, so it's still quite bright. It's currently called a white dwarf, but I think that's politically incorrect, and I'm told the name is going to change to neutral colored, dimensionally challenged object in the near future. More massive stars produce the elements up to iron, and when they come to the end of their lives, they blow up in a supernova. and they leave behind something. It's actually this lower right dot there. And that's called a neutron star because it's basically highly dense. It's about 10 kilometers in diameter, in radius rather, 20 kilometers across, made up largely of neutrons. But they have an enormous magnetic field and they spin very rapidly. And amazingly, you can get beams of radio waves and even sometimes light that come out along the magnetic field axes. And these we call pulsars because they give you very regular pulses of energy. And that's just a sort of simulation of what goes on. If we happen to lie in the right direction, our telescopes can pick these up and we can actually measure the rotation rate, the rate at which they slow down, and all sorts of things about them which teach us about the properties of these objects we call pulsars. Sorry, I've got to do this to move on. Now, there's a problem. The space between the pulsars and us is not a vacuum. So you get dispersion. That the pulse at a lower frequency arrives before the pulse at a higher frequency. If you try and increase the bandwidth of your system to increase your signal to noise ratio, you just blur the pulse out. So what you have to do is to separate into many short, narrow bandwidths. And we've actually gone up to 256 narrow bandwidths. And someone spent about 2 years building all the filters to do that. So what we do is, or we did, because it's all down by computer, we actually had we received the signal at a certain time here, at that point, and then, and then another one down here. So the idea is to add all of these together to integrate the signal. Now, this is how we did it. You have a filter, one of these very narrow band filters. We then have a square law detector. We converted that output into a frequency, and that went into a counter. So when the counter was enabled, it would count up the frequency derived from that system. And there were a whole bank of these, in fact, up to 256. And what happened was, when the pulse arrived at the one on the left, it integrated up. When it moved into the next filter band here, we transferred that number into here and carried on integrating, and so on and so on and so on. So gradually we followed the pulse, and that meant we could have much broader bandwidths and get much better signals. And I had to design and build that sort of kit, which was great fun. Okay, we are very good. Our Lovell telescope is observing pulsars we know about. It's not so good at detecting them, and we don't see the Milky Way very well, but they see it much better at the Parkes telescope in New South Wales, Australia. And we built a 13-beam receiver for them. You can see it being winched up to the focus there. And together, we discovered many, many more new pulsars. All those ones that are red were new. Amongst them, using a supercomputer at Jodrell, I think the Alliant, we were able to show that one of these wasn't one pulsar, but two co-rotating pulsars, which that's tried to simulate. They're apart about the diameter of the sun, rotating one around the other. I'll stop doing that because it will make you go hazy. Now, Einstein, come back to him again, he says if you have two co-rotating massive objects, they will emit gravitational waves. That takes energy out of the system. So if they're there, these two objects should gradually get closer together to lose their energy of rotation, and that gets converted to gravitational wave energy. It was computed that these two neutron stars each day would get closer by 7 millimeters, and our telescope could detect that precisely. It's in fact probably the best test bed for studying Einstein's theories of special relativity that we currently have. And for that work, we were actually given what's called the Descartes Prize, which actually is worth more than the Nobel Prize. It was for a group, it's not for any individual people. So there we go again. I shall move on to the next one. Now, this is a simulation. The green grid is space-time, and you can see a sort of a ripple there. As these two neutron stars co-rotate, they form ripples in space-time that work out through space at the speed of light. As they get closer together, they speed up, and so the ripples get closer and closer together. And I'll try and run this now. Hopefully that will work. Here we go. You can perhaps see some ripples working their way outwards. When they get very close, the ripples get very close together. It's called a chirp, and eventually they will coalesce into one. At that point, you get what you can call a gravitational wave tsunami. You can see it going out there. And in fact, we also think you get a gamma ray burst and probably a black hole results. So that's what theoretically predicted. I'm sorry, again, I have to move on. Now, that's the gamma ray burst. For some reason, I don't know how, but they reckon that that should be 2 seconds after the gravitational wave. It's probably because the wave comes as the two hearts coalesce, and the actual gamma ray pulse takes some time to sort of get to the surface and be emitted. I'm not too sure on that. Okay, I'm sure you may have heard of LIGO, the Laser Interferometer Gravitational Wave Observatory. There were initially two, one at Hanford in Oregon and Livingston down in Louisiana. They have these two pipes containing a highly evacuated, well, actually the channels contain a pipe which is highly evacuated, along which laser beams travel back and forth, giving an equivalent length of about 127 kilometers. Now, they set them up, the light from one source goes down the two beams, comes back, and they set it up so they're in anti-phase, so there's no signal. If a gravitational wave happens to come, it will momentarily shorten one arm and lengthen the other. The two get out of phase, and that can be detected. So that's how it aimed to detect gravitational waves. And it first of all did detect some coalescing of some fairly massive black holes. But I just want to, that's the one at Hanford, I might say. And then later, the Italians, who are very good astronomers actually and physicists, I take my hat off them. They built Virgo, similar, not quite as large, near Pisa in Italy. On the 14th of August 2017, they detected the gravitational waves produced as two neutron stars merged. And those are the detections. The Virgo one, of course, being a less sensitive instrument, is not so good, but they work perfectly. The great thing was, because there were 3 of them operational, they could actually locate approximately where the gravitational wave came from. That was the chirp, and that's exactly what they saw. And that final little spike there is when they two coalesce into a black hole. And as predicted, we shall see a gamma ray burst appeared. And that was discovered or measured by the Fermi spacecraft, a gamma ray telescope. There is, in fact, the signal from LIGO here, and there is, in fact, the gamma ray burst precisely 2 seconds afterwards. So it's the first time anything has been seen simultaneously in both the electromagnetic spectrum and also in gravitational waves. So a wonderful experiment. Because there were 3 detections, they were able to say roughly where it was, and looking there, it was found that in a distant galaxy called SSS 17A, there in fact was the neutron star remnant, now a black hole. Well, Berlin, as I said, was greatly extended in the 90s, and I was the project engineer for that for a while. I had to give up teaching for a bit to do that with this lovely telescope at Cambridge. And that's the system we currently have, although we hope to extend it before too long. The control computers were updated to what's called a Microvax. You may remember those. And the only one that wasn't updated was my little Micro-Circe in the phase measurement system. And that was upgraded. I doubled its speed. There were later chips and much better memory systems for it. And that remained in use, as I said, till 2018. At that time, after that, the Lovell was showing real signs of age. And we got a grant by the Millennium Commission to take the original surface off, which was decaying, and replace it. And there they're in the process of doing that. Partway through it looked rather good. This was the new part. They trial painted that bit, and here they'd done alternate panels. Now the rust is looking very bad because I took this picture at dawn, in fact on the 2nd of January of that year, and so it's looking a bit worse than it really was. But look at the difference. This is a hologram of the surface measurements. It should be a uniform mid-blue. On the left is how it was. And there's obviously one little ring here that was really out. This is how it was done after the first iteration. And we haven't yet bothered to do a second iteration. So that telescope surface is now vastly better. than it was. It's a new surface. It looks lovely. A new drive and control system was introduced. And in fact, on the telescope structure, there are actually 10 microcomputers linking together and basically making all the motors run together in synchronism. So it's now a vastly better drive system. I promise you, hand on heart, which you can't see, that telescope is now better than at any time in its life. In fact, it has just completed its third upgrade when we replaced the original surface, which was in danger of breaking apart, with a new one. So it really is still a front rank instrument. It's still the third largest fully steerable telescope in the world. And that's its new control room with these lovely display systems here and here. And in fact, you'll see one again in a minute of how we can control it. And we're now controlling the telescopes using a VME bus system. You can see a picture of one of them there. And this is one of the lovely control streams that's been produced by one of my colleagues, Roger Noble. And you've now got a lovely idea of what's actually going on across the whole system. We were given the grant of about £8 million, about 2002. And that was to replace those microwave links with a limited bandwidth between our telescopes with a fiber optic system. That shows you the layout of the system, coming first into Birmingham, then up to Crewe, and then back to Jodrell. That actually shows you what we had in the control cabin of each telescope. The band came in, was digitized, and then it was converted into 3 colors to color multiplex onto a fiber. Each of those was 10 gigabits in bandwidth, in data. So each of those telescopes can send us back 30 gigabits of data per second. And that shows you the whole layout, which was quite amazing. And I'm staggered it works, but it really does. And we also were able to do the phase measurement over the same system. So it now has high sensitivity, very high resolution. It's probably the second most sensitive telescope in the world, and it can do some wonderful things. That's actually just a picture of that double quasar, showing you this is the jet coming out from the main one. You don't see the jet from the gravitationally lensed one down there. But this is interesting. A couple of years ago, we took an image of Betelgeuse, and it's not just a point. We can actually see it's actually not even a uniform sphere. It's been outflowing material. And some of you may remember that around last Christmas, it dimmed by 1.5 magnitudes. People thought it might be about to blow up. It turns out it ejected a great cloud of dust which obscured the light. That's gradually dispersed into space. It's now back to its original magnitude. But we've seen what's been going on with E. Merlin. And we did a lot of work with the Hubble Deep Field. Optical telescopes can't measure positions accurately, but we can. And we were able to locate precisely where all of those galaxies were. We could only actually measure the positions of the brightest, but that gave us the key to the whole thing. And that was very, very helpful to the result, the following up data, And we're now investigating many of those distant galaxies to learn about the evolution of galaxies way back in the early universe. We're hoping to extend Merlin to Goonhilly. You remember that's the ground station that we had, and that telescope there, which actually was a copy of the Mark II telescope, but with a round dish, and that was used to bring back the signals from Telstar. Some of you may remember way back in time. So we're hoping to add those in the next year or so, and that will double the size of Merlin, double its resolution. Now, finally, we have a role, the Hubble telescope and particularly the Cambridge telescope, in what's called the European VLBI network. I like to call it the European telescope. And it stretches, as you'll see, all across Europe. Final example, this is a pair of interacting galaxies, M81 and M82. You can actually image them quite easily with a small telescope. But M82 has been passed by M81. It caused an amazing burst of star formation. It's called a starburst galaxy. And many of those stars, very massive stars, are now blowing up, forming supernovae. And all the stuff gets blown out, as you can see in this picture. But you cannot see what's going on visually. There's too much dust obscuring the center. And I'll just have a little quick drink of water. But with Merlin, we can actually look at the heart of it. And all those white blobs are supernova. supernovae, and we can actually measure their expansion rate. But we'd like to do better. By linking together our telescopes in the UK, and we're now actually using many of the Merlin ones, as well as the Cambridge Mark II and Lovell, with telescopes across Europe. I don't think we're using the one in the Crimea anymore, but there are now 3 actually in Italy, one near Bologna, one in Sicily, and there's one in Sardinia, which I think is that one. I'm never quite sure which is. So, as I said, the Italians are brilliant astronomers. I take my hat. There's 2 in Spain. There's one here in Germany. There's one here in Poland there, and a couple up here, Finland and Sweden. Notice a hole here. For some reason, the French don't seem to want to know. And in fact, they could have a telescope here on the Cherbourg Peninsula, which could be linked into Merlin, and that would be a wonderful instrument. And why they just do their own thing, I just do not know. Anyway, we used to, at each observatory, record the data on these enormous great tape decks. I think they were used by GCHQ for a while. Then we used arrays of disks, but now that's our new observing room. It's been updated. The data is just transferred almost directly by fiber to the place in Groningen, Holland, where they actually do all the analysis. And that's a picture of it as when they had all those tape decks. But I can't find a more modern picture of how it looks because they don't seem to bother to put one on the web. So there we go. So that can produce the most detailed radio images, and I think the most detailed, highest resolution images of almost anything. And it shows back in time the evolution of a supernova over a couple of years becoming this shell. It's amazing. We can actually study objects in detail in an object that's 12.5 million light years away. So finally, I plotted this chart some years ago. If when the Lovell telescope was first built as the Mark I, it had a sensitivity of 1, it's now a lot better than that, of course. The Effelsberg dish in Germany would have been about 8. The VLA, the very large array in America, which is an array of dishes, would have been about 100, a lot better. And then that was actually beaten by the Arecibo telescope in Puerto Rico. But now that we've made Merlin E-Merlin, and the EVLA has made the EVLA using exactly the same correlator system and fiber systems, we've now got 2 telescopes that are almost the same sensitivity. And together, it makes the most fantastic and probably the best radio instrument in the world. So that's really, really good. And I'm very proud to have been a part of the design and building of Merlin way back in the last century now. But we want to do better. And no one country could actually build something to exceed what they could do. And so the world is getting together to build what's called a square kilometer array. And the main part will be built in the Karoo of South Africa. And that's just a view of some of the telescopes that will be on the ground there. The global headquarters are very pleasingly, in a way, at Jodrell Bank. That was why it was being built. It's now complete. It was opened about a year ago. This is it. It now totally envelops. There's our little observatory here. And we're now totally outclassed, but we still like living here. I haven't been able to go there since the start of lockdown. It's on a need-to-know basis. I'm still, in fact, an honorary, I still work there. I do things for the observatory. In fact, a year or so ago, I built a little pulsar receiver for a student telescope based on an Arduino Duo microprocessor. And that actually works very well. And they're now going to build one of these in Brazil for a system out there because it's a bit of fun. Anyway, so I'm still involved, and we have a nice meeting every Wednesday of all the elderly people like me just to see how we're getting on together. So there we go. So that's the SK Global Headquarters. Building of the array will start formally, I think, this year, end of this year. It's been delayed a bit by COVID, but perhaps next year. And the first phase should be operational by about 2024, 2025. And that will be very exciting. Now, I hope that's given you an idea about what's happened at Jodrell over the years and a bit about the computers that have been used to make it work. I should just say that you shouldn't thank me for this talk, but Sir Bernard Lovell, who sadly died a few years ago, without whose vision none of this would have been possible. So thank you for listening. Now, I have no idea at the moment how to get out of my show and how to get back into, can I get back in?
Here we go. I shall help you out in.
Yes, can you get me back in so people can perhaps see me? That would be
I
nice.
can indeed. So please do send your questions through.
Share my webcam.
There we are.
Oh, good. That's great.
There we are.
Okay, you can see a very nice painting of the Lovell telescope behind me, I hope. So I'm in my little studio now. I've set this up specifically for doing some of these Zoom and webinar meetings.
That's it. So if you could possibly stop sharing your screen, that would hopefully mean that you can see more of our faces.
How do I share? Stop that. I don't see anything to say stop sharing. I'm very used to Zoom, but not so much to this. There's a sharing. No, that's that, a webcam. I don't see how to do that. I'm sorry. Well, what can I do?
Don't worry about it for the time being. Don't worry.
Help. There's nothing that says remove your screen. Supposing I just do that. Does that help?
No, don't. Honestly, let's not worry too much. I'm just thinking in terms of any questions that's coming through. We haven't had any questions as yet, but I suppose I have a couple myself.
I must have bamboozled you all, but go ahead.
Well, firstly, I'd just like to say that my mind was blown throughout most of that, and certainly I was fascinated throughout. Now, one of the things that I suppose I had thought about throughout was that across your career, I'm sure you've been in the position where you have been a key person dependency. And I'm sure that things like knowledge transfer and sharing have been very important. And I suppose coming from more of a typical IT type background, that's always planned for, and there's always groups and sharing. But is that the same for your career? And have you had people alongside shadowing you?
Well, not really, because we didn't have any people. Honestly, the team at Jodrell was very, very small, and the number of engineers, and I have to say for a while, I was in fact, I suppose, a computer engineer in a way. But in fact, that was a sad thing because I really wanted to be an astronomer. All the lecture courses I gave at university were about electronics and computing and programming because they needed people to do that, and there weren't that many people in the physics department that could. Finally, 6 years before I retired, they let me give a wonderful course. Well, I loved it. A course on Introduction to Astronomy and Cosmology to all the first year, because astronomy is a wonderful way of showcasing physics. I could even get some quantum mechanics into it, believe it or not. And in fact, that became a textbook, which has earned me quite a bit of money over the years. So that was really good. So I wasn't really allowed to be a lecturer in astronomy until the very end, but I was allowed out to do a fair bit of astronomy over time. But I spent a lot of time, as you've heard, having to do some of the work to make Jodrell work. And I'm quite pleased I did that. So that's something.
Absolutely.
Again, but I would say that when you saw E. Merlin, when we got the grant for that, there was in fact an analysis done, and I was one of the people on, I forget what they call them, but they had to worry about slightly, just in case. I was getting old by then.
We've had a couple of questions through, so I'm just going to read them out. So, is Brexit going to have much impact on the UK participation of the EU telescope network?
Now that's interesting. Well, the first two good things are that ESA, the European Southern Observatory, which has its major telescopes down in Chile, and also that's ESO, I'm sorry, and ESA, which is the European Space Agency, are not part of the EU, and we contribute to those independently and will remain part of them. And in fact, the SKA is also an independent unit which is funded by a consortium of about 20 countries. I think the final verification of that is going through. Each country has got to have it. I forget what the word is, but anyway, agreed, and that's currently going through at the moment. So Brexit doesn't actually affect that. There's one thing that's a little bit worrying, is that the UK and particularly Jodrell Bank, we've been very good at getting income out of the European EU Science Fund. And I think that's funded about a third of our budget over the last few years. Now, that in principle will stop. Now, whether our own country would fill the gap, I don't know. But I think we are actually hoping to still remain in that part of the EU, fund that, just contribute to that. And so hopefully we might still get our funding. So cross fingers, hopefully Brexit will not affect us too much. But that is cross fingers.
So one of our next questions is around after fiber optics, what's next?
Oh, I don't think anything is next. There's no real way we can actually increase the bandwidth of Merlin. We can't actually make our receivers any better now. They're essentially as good as the laws of physics allow you to make. And some of you may know about the Planck spacecraft that went up to actually measure what's called the cosmic microwave background and tell us an awful lot about the universe. Our receiver lab actually built quite a number of the receivers for that because they were state of art. So there's not a lot we can do. You can either basically build bigger telescopes, and we can't really afford to do that. But as I said, we are hoping to double the size of Merlin with those 2 telescopes at Goonhilly Down, and that's really the best we can do. But of course, we are contributing quite a lot to the Square Kilometre Array. It's using some of the technology we've developed here at Jodrell Bank. We are in fact an SKA Pathfinder to help its development, and we received some funding in fact for that. So there's still a bright future, and the fact that their headquarters is at Jodrell Bank should mean that the site remains viable for many years to come. And honestly, there's no reason why that Lovell telescope shouldn't still continue as a front-rank world instrument along with Merlin for quite a long time to come. I mean, it's been around for a very long time, a bit like the Forth Bridge, but there's nothing to say the Forth Bridge won't be around for a lot longer. So let's keep hoping.
Fair enough. So one of our next questions is around what kind of telescope do you have?
Oh boy, yeah, that's interesting. Well, look, I did say I wanted to be an astronomer. I had to wear very thick glasses when I was about 11. I don't wear them anymore. I'm not wearing them now, although I do actually use them to see a computer screen well, because about a year ago I was given 2 new lenses. My cataracts removed. But the optician in our little village near a town of last resort called Bognor Regis was a great friend of my dad, and he gave me lenses. In fact, 1 or 2 I've still got, and I made little telescopes with cardboard tubes, and I honestly do remember seeing the moons of Jupiter and I think the crater on the moon. There are some things that burn in your memory, and I can actually visualize holding this tube up out of the front window of our house in Feltham, only 100 yards from the sea, so it was very dark. And that got me hooked. And I had quite a few books bought for me during my teenage years. I was able to do, I need a bit of water again, sorry.
No problem.
A short course on astronomy at Oxford, along with my physics and mathematics. I was also very keen on radios. I was in the Signals radio corps there, and I was actually, I had a PIP and did some work with radio relay troops in Germany for a while. And so when the final exams were coming up, I didn't really know what I was going to do. I thought I might go into the Royal Signals, and I easily could have done that. But I saw an advert on the stairs of the Science Library saying, come and read radio astronomy at Jodrell Bank. I liked astronomy, I liked radio, that was it. Now, in fact, by about a few years later, I was actually able to buy a 10-inch telescope. And not many people had them that size in those days. And I've gradually expanded the telescopes that I have. I've written about them quite a lot. Since I retired, I've written 3 books on amateur radio astronomy, and someone said I'd now become a professional amateur astronomer. I helped found our Macclesfield Society in 30 years ago now, and I was president of one of the UK societies for some time as well. So it's been a major part of my life, and I shouldn't say this. I got quite excited 4 days ago, because we saw the first decent sunspot group of the next solar cycle. And I'm afraid that made me find on the web a very expensive edition to my solar telescope to make it twice as good, probably twice the price actually, and that's due to arrive by one of the carriers, DPD, is it tomorrow morning? So I'm looking forward to that. It does actually slightly worry me. Solar cycles are 11 years in length. This could well be the last one I can ever observe. So I thought I'd try and do it as well as I can.
The fact that you're still getting excited about it is the main thing.
Oh yes. And I have a blog. I don't call it a blog. It's called a digest. If you put Astronomy Digest into Google, you'll find it. And I think I've now, over the last 3 years, written about 100 articles about different aspects of amateur photography, amateur astronomy. Some about astrophotography, which I'm very keen on and do a lot of. So it's a major part of my life now, since I've retired, probably even more so than when I was working full time.
Fantastic. So we're getting questions through thick and fast now, so I'll try and get through as many as I can.
In my replies.
No, don't worry. So does Jodrell still record reports of UFOs?
We never have, honestly.
Okay.
Some people thought we did. We never did. Look, I give a talk, and I actually was a project scientist in the UK for what's called Project Phoenix, which is the most sensitive search for ET ever undertaken. But we could only look about 200 light years away, so we couldn't expect to pick up any signals. I give a talk, I was actually giving it this morning, on the search for life beyond the Earth. And my conclusion, along with many of my colleagues, is that I won't say certainly, but very probably, at the present time, we are the only advanced civilization in our Milky Way galaxy. The probability of getting advanced life is very low. Simple life forms, very widespread, I suspect, but advanced like us, very, very, very rare. So I'm not worried about UFOs. I have seen a good one. It was in the Manchester Evening News front page. I'd actually been giving a lecture in Prestwich, north of Manchester. I was coming home and I saw this glowing orb in the sky moving silently across. But I had binoculars with me and I used them, and I saw it was actually a hot air balloon. This was at 10 o'clock at night, mark you, going over Manchester. So that's the nearest thing I've seen to a UFO, but I honestly don't expect that we'll ever see any real. I mean, look, UFO's fine. Unidentified flying object. That could be anything. Okay.
Very much so. So in terms of, do you see that there's a prominent role for sort of artificial intelligence in astronomy in its future, or more so in its future, for things like detecting and classifying galaxies?
I think that's absolutely right. It's going to take over many, many aspects of life. Now, this is only happening now, and I'm a bit out of that side of it, to be honest now, but I'm sure it will work. People have been actually analyzing galaxies. They've had people at home doing it, and that's been wonderful. But now you could actually show all these images to a computer system, and it could do some wonderful things. So it is going to be a major addition to the armory of tools that we have. So that's something good for the future. And obviously computing is a major part of that.
Okay. And did you get to name any interplanetary objects?
Well, no one can name anything themselves, but very nicely, in fact, on my 60th birthday, which is a while ago now, 70 years ago, I was sent a plaque because the International Astronomical Union, which is the professional body of astronomers, have actually named an asteroid after me. It's called Ian Morrison. There's no dash in it. It's only about eight kilometers across. It's quite small, but anyway, it's something that will be there forever, which is rather nice. So that is to some extent true.
Excellent. And then, so we've had another big question. So, how big is the universe, and how old is it?
Well, right. Age is quite easy. From the observations made by Planck, and Jodrell Link was very much involved with that. In fact, our team leader got the CBE for his work in it. We now know the age of the universe is about 13.84 billion years old. And that's pretty precise, isn't it? It's quite amazing. So that's fantastic. Now, that means we can only see out into the universe that distance in light years. So that makes sense. We can't see anything that the light hasn't reached us from. The universe has been expanding the whole time, and all we can do is really guesstimate its current size. And I think they're sort of saying about 54 billion light years across at the present time, but getting ever bigger. Does that make sense?
Does. Fantastic,
Good.
thank you. Again, I'll just carry on. Bearing in mind, I might not know anything about these. I'm just reading them. So
that's fine. Go ahead.
So is Jodrell Bank suffering from radio noise terrestrial interference?
Oh boy. Well, the answer, of course, is yes. And of
So
course,
you say of course, but you've got mobile phones, which are terrible. You've got satellite television. We've now got Erwin Musk we've got to contend with. Elon, yeah.
Elon Musk, that's right. It's getting worse the whole time. In fact, there are many things we can no longer do with our telescopes that we could in the past. However, there are two things that we can still do very well. First of all, the Lovell telescope and our Mark II sometimes, and a 50-foot telescope, 13-meter I should say, can observe pulsars. Because we know precisely what we're looking for, we can make what's called a match filter. Does that make any sense? And that enables the computers to eliminate anything that isn't right. So that works. Secondly, with Merlin, unless a signal is strong enough to overload the front-end amplifiers, the amplifiers in our focus boxes, and we try and make them have very large dynamic range so they don't get overwhelmed, then signals have to correlate across the whole of the Merlin array. And of course, unless they're very, very far away, that cannot happen. Does that make sense too? So we're still okay. Now, I would say, I think I said, you would not build the Lovell telescope where it is now, but there is one good thing about its location in Cheshire, which didn't really strike me for a long time. It is somewhere in the UK that probably has the lowest average snowfall per year. I've been there for, I think it's 56 years now. I've never seen more than about 4 inches of snow on the ground. Yet when I've tried to drive back into Macclesfield, I've run into a snowdrift. That's because the snow that comes from the southwest gets caught by the mountains in Snowdonia. That comes from the east tends to be picked up by the Pennines. We are in a snow valley. And snow is a problem because we can't move the telescope when it's coming, usually. So it will build up in the dish, and that makes it quite heavy after a while. And we have to pray that there's a bit of sun sometime. We can tilt the dish so the sun can melt the snow and it comes out as a big avalanche, which is quite impressive to watch. So in that respect, its location is not too bad.
Fair enough. In terms of how people can get in touch with you, and you've mentioned your digest already, but we've had somebody also mention that they're a member of the North Wales Astronomy Society, and they would love for you to be able to present there as well. So is there an easy way?
Well, I think I've spoken to them a couple of times actually, and I love going out there, and usually stay overnight as well, which is good. Yes. To be honest, my email address isn't actually widely known, but it's in fact, I'm happy to give it out. It's very, very simple. It is Ian, that's IAN, at morrison.net, Ian at morrison.net. Now, notice, if you saw on that first slide, I've only got one R. Our little group of Morrisons is a bit rare. There are a few. The guy that invented the Times New Roman font was a Morrison, as it happened. In fact, I got very worried. In fact, 2 years ago, I discovered something I wasn't very happy with. I don't know if you know where Donald Trump's mother came from, but she came from the village of Tongue in the Isle of Lewis, 4 miles from where my family comes from. I just hope there wasn't too much interbreeding in those days. This was a long time back. Anyway, so Ian at morrison.com, you can happily email me and I'll do my best to reply. Does that help?
It does indeed. Well, look, we've got no more questions coming, and I just wanted to thank you for your time tonight, because I certainly found this an incredible talk, and I'm sure everybody else has as well. We've also had a few people mention that they've thoroughly enjoyed it, so thank you very much.
My pleasure. Good to see you all, and I hope next time, Sunday, we can meet again.
Absolutely. Well, thank you all very much, and if there's any questions, please feel free to send them through. But other than that, I wish you all well, and we shall see you all soon.
Bye, everybody.
Thank you very much.